Okay, so the power functions here are, I guess function is maybe the wrong word, but just power maps or something. We can define for any alpha in the complex numbers and for z non-zero, we define z to the alpha to be what the formula that's familiar from real numbers, e to the alpha log z, where we use lowercase log. So again, this is a set valued object. So it's all values e to the alpha w over all w's such that e to the w equals z. So as I wrote here, this is multiple valued when alpha is not an integer. It's single valued if alpha is an integer, because if I have alpha equal to some integer, then in the exponent I have n log z, and maybe the way you'd compute this is you'd have like a particular value of the logarithm, say the principal one, and then all others are obtained as multiples of 2 pi I, and so an integer multiple of this integer multiple will still be an integer multiple, and so there's no multiple values here because e to 2 pi I will always give me 1. It's interesting to do something a little silly, which is see what this means for computing something like I to the I. So the definition of this is e to the I times little log of I. And what is little log of I? Well, it's natural log modulus of little I plus I times the argument of I. Well, this is 1, so it's natural log of 1 is 0. And the argument of I is, well, it's 90 degrees, so it's pi over 2 plus multiples of 2 pi. And that's what we've written here. But we have I squared in there, so you get a minus pi over 2 in the exponent, and then you get all of these e to the 2 pi z's here as the other values of this multiple valued object. So it's e to the minus pi over 2, e to the 2 pi n, or n is in z. But as with log, we usually restrict to branches of power functions, because if you're going to use this maybe to study power functions in the real numbers, you usually confine yourself to a branch. And so here's just an example of a branch. I don't want to repeat all the definitions of branches. I hope you get the idea by now, but the principal branch of one of these power functions would be just e to the alpha capital log z, which would be defined on the plane minus these negative numbers here. And this will be holomorphic because we prove that the principal log is holomorphic. So a particular interesting example of a principal power is the principal square root. So I'll just write it with this notation, but you do have to keep in mind, generally this is ambiguous, and so you should, if someone says z to the 1/2, you ask them which branch are you taking. And so here I'm writing the principal square root, which by definition is this, e to the 1/2 principal log of z. So it's defined again on the same set that I mentioned, and it maps the plane minus this ray onto the right half plane, because we're taking 1/2 of the log here. So all of the arguments are getting hit with a 1/2. All of these arguments live in the interval minus pi to pi. So taking 1/2 of those will be between minus pi over 2 to pi over 2, and so we only get points in the right half plane, which is point z, such that the real part is positive. And you think of the square root function as taking the plane minus this ray, and you're kind of moving the two sides of the ray over to get the right half plane. And so you're smashing it onto here. And you could consider other principal roots in a similar way, and that's a good thing to think about. The last thing we'll mention in this video series about the exponential function and its friends is the trig functions. So we've already defined cosine and sine for real numbers, but we can use what we've been doing to extend them to complex numbers. So we'll define cosine of z, where z is now a complex number, in a manner that's analogous to what we had for real numbers. So it'll be e to the iz plus e to the minus iz all over 2. And this gives the familiar power series that you learn in calculus for cosine. We define sine of z to be e to the iz minus e to the minus iz over 2I, and you get another familiar power series. Notice you can think about these functions in the entire complex plane. They're not going to be bounded by 1 or anything. I mean, they'll go to infinity in certain directions. In particular, if I plug in something like cosine of minus it, what do I get in here? I'll have e to the t plus e to the minus t over 2. So this is actually a hyperbolic cosine, but as t goes to infinity in the real numbers, it'll blow up. So it doesn't satisfy all the properties of cosine, but it does restrict to the usual cosine when I put in a real number for z. A couple things to point out is that cosine of z equals 0 if and only if, well, we can just solve for it if we factor out e to the minus iz in the expression. And we see that this is 0 exactly when e to the 2iz is negative 1, and so you have 2z is pi plus multiples of 2 pi, so z has to be pi over 2 plus pi times an integer. And so the zeros are exactly the same as for real values. It doesn't pick up any extra zeros. The same thing happens with sine. I don't need to go through the same argument. Sine of z is 0 exactly when z is integer multiple of pi. Okay, and then we can define other trig functions just based off of these, and they'll be holomorphic whenever they're defined. So tangent of z will be defined as sine over cosine, and it's defined whenever cosine is non-zero. Cotangent is defined whenever sine is not 0, and you can define cosine and secant in a similar way. And this concludes the video series on the exponential function. So I hope it was fun to learn that from the exponential come the trig functions, which and also the logarithmic functions, and also power functions. So they're all just built from the exponential. So all of the standard functions are based in the exponential function.